everyone, welcome back. In this video, I will introduce you to buffers. So what do buffers do? Well, they resist the pH change by neutralizing any added acid or base. Typically, they consist of a weak acid and its conjugate base. Or you can think of it as a weak base and its conjugate acid. Essentially, they are weak acid, weak base conjugate pairs, right? And what the weak acid does, its job is to neutralize added base. And the conjugate base's job is to neutralize added acid. Let's talk about the buffer system in the blood, which has carbonic acid in it. So the carbonic acid is the weak acid portion of the buffer system. And if I'm adding base, essentially I'm adding hydroxide ions. Remember, a Bronsted base is a proton acceptor, and a Bronsted acid is a proton donor. So the hydroxide will take the proton from carbonic acid to make the conjugate base of carbonic acid, which is bicarbonate. So now it's missing a proton, so now it has a negative formal charge. It's the bicarbonate polyatomic ion and the conjugate base of carbonic acid. And since the base took a proton, it went from hydroxide to the conjugate acid of hydroxide, which is water. Now the buffer system also has to have the conjugate base present. So that is bicarbonate, the conjugate base of carbonic acid. I use Cb to represent conjugate base. Added acid means that we are adding the hydronium ions. That represents the added acid. Bicarbonate is acting as a base. It's accepting a proton and it turns into H2CO3. It's conjugate acid, carbonic acid. And the hydronium ion and the acid's donating that proton, so it goes back to the conjugate base of the hydronium ion, which is water. And so when you're making a buffer in the laboratory, remember that you must have a weak acid and the conjugate base together to create the buffer solution. So in this figure here, the acetic acid is the weak acid, and the sodium acetate is the weak base. Remember that you can't just buy acetate, which is the conjugate base of acetic acid. You have to buy it as its salt. But we've learned in a previous video that sodium doesn't affect the pH. It is a cation and a counter ion of a strong base, so it's pH neutral. And so really what's going to help us out with the buffer here is the acetate, the conjugate base of acetic acid. So in summary, a buffer consists of a weak acid, which can neutralize added base, and the conjugate base, which can neutralize the added acid. So let's do a learning check together. Which of these solutions is a buffer? Is it A, 0.1 molar HNO2 and 0.1 molar NaNO3? Is it B, 0.100 molar HNO2 and 0.1 molar NaCl? Is it C, 0.100 molar HNO2 and 0.100 molar NaNO2? Or is the answer D, 0.100 molar HNO2 and 0.100 molar HCl? Excellent. The answer is C. Now let's talk about why A, B, and D are not the correct answers. So A is not correct because nitrate is the conjugate base of nitric acid, HNO3. Nitrous acid, HNO2, is a weak acid. So that works out for the buffer system, but we need the conjugate base for the nitrous acid, HNO2. So that's why it's not A. B has the nitrous acid as a weak acid, but sodium chloride, which we're looking at just the chloride itself, is the conjugate base of a strong acid, hydrochloric acid, HCl. So that's not going to work either. Part C, now we have the nitrous acid and its conjugate base, nitrate. And so that checks out. You have a weak acid and its conjugate base. This is a good buffer system. Let's look as why D is not the answer. We have nitrous acid, weak acid, but we also have HCl, which is a strong acid. And so both of these, and there's no conjugate base. There's no weak conjugate base to work with here to neutralize added acid. So this is a poor buffer system as well. So whenever you're preparing a buffer, you need to use a weak acid and its conjugate base. So in this case here, C was the answer, nitrous HNO2 acid and the sodium nitrite NaNO2. Thank you all for watching, and I'll see you next time.